Millions of years ago, an 18-meter-long predator known as Megalodon roamed the world's oceans. But how did this shark achieve such a large size? How did it become extinct? Research conducted by Dr. Catalina Pimiento has provided us with the answers to these questions, revealing an unrecognized mass extinction that resulted in a permanent shift in all megafauna within the oceans. In contrast with the effects of the extinction of small organisms like invertebrates, this extinction event resulted in an important erosion of functional diversity, leaving communities highly susceptible to future extinctions. The study of such systems is essential in understanding how the loss of apex predators can destabilize entire food webs, especially with the problem of overfishing we see today. So let's dive in and swim with the sharks. Megalodon lived approximately 2.3 to 2.6 million years ago. It is thought to have gone extinct near the beginning of the Pliocene era. It may have looked like a stocky version of the great white shark, although this is hard to prove as we only have vertebra and teeth fossils to go on. So how did it get so big? There is a strong link between trophic level and giganticism within the ocean. However, filter feeders and mesotherms appear free of this trend. As Megalodon was not a filter feeder, it is likely that filter feeding evolved after acquiring mesothermy and was the surviving method of giganticism. Catalina has hypothesized that the diversity of large marine creatures at the time provided substantial food for Megalodon, with larger creatures capturing more food being the driving force behind the evolution of its great size. Fossil evidence and computer models support Catalina's hypothesis that Megalodon grew larger and larger over the generations, hinting at selection process for a larger body size, reaching its peak size just before extinction. Using a computer modeling tool, Pyrate, rates and ranges of the extinction could be calculated, revealing that the loss of Megalodon actually coincided with the loss of 1/3 of other marine megafauna, confirming an extinction-level event. Megalodon faced competition from whale-eating cetaceans, such as ancient killer whales, which likely contributed to its extinction. It was initially believed that a preference of warmer waters likely resulted in the extinction. However, whilst it is thought the oceanic cooling associated with the onset of the Ice Age may have impacted shark numbers, it is unlikely the real trigger behind the loss of the shark. If it were, we would expect poikilothermic animals to be impacted more severely. The surviving turtle and ray species show this was not the case. Catalina's team have already identified possible Megalodon nurseries within lowland areas of Peru, areas that would have become inaccessible during lower sea levels. As the sea lowered, Megalodon would have been forced further out into the oceans, meaning their young would have struggled to find necessary levels of food demanded of such great size. A reduction in the diversity of baleen whales and a shift in their distribution towards polar regions may also have reduced Megalodon's primary food source. The extinction of the shark appeared to affect other animals. For example, the size of baleen whales increased significantly after the shark had disappeared, as well as being the emergence of the giant whale species such as the blue whale and sperm whales. Megalodon has captured the attention of the world. Its size and power are truly something to respect, yet the lesson of its extinction may be far more valuable. Catalina's research has shown that the loss of an apex predator such as this can have catastrophic impacts on the entire marine food web, resulting in large-scale restructuring and re-establishment of lost niches. As such, it is essential that we guarantee the continuous survival of orcas, great whites and other apex predators to ensure the stability of the world's oceans and protect against other megafauna extinctions.